Good morning, ladies and gentlemen. It's my pleasure to introduce my research here. The title of my presentation is Collaborative Path Optimization Method for Fluid Control Material Storage. My presentation includes 4 parts: introduction, algorithm design, the simulation results, and the conclusion. With the development of logistic industry, intelligent storage has attracted more and more attention. The characteristics of storehouses for fluid control materials are obvious. Compared with the common warehouse, the sudden fluid situation and the emergency of disaster relief make the warehouse of fluid control materials have high requirements on the efficiency of outbound, but not excessive requirements on the efficiency of inbound. At the same time, the classification of fluid control materials and goods placement is also a factor affecting efficiency. The 3 problems to be solved in this article are building warehouse model, building clearing avoidance system, and building intelligent avoidance algorithm. In view of the 3 problems to be solved, the following work is carried out respectively. They are establishing storage model of fluid control materials, collaborative optimization of multi-robot collision avoidance, and achieving intelligent avoidance. This chapter processes an efficient storage model to meet the storage requirements of different regions and materials. The small-scale storage model is adopted here, with a planned standard warehouse of 25 meters long and 29 meters wide. The most left row of the warehouse is the position of the picking table. The robot starts from the picking table, moves to the corresponding shelf to taking down the goods, and sends the good to the picking table, which is the end of the warehousing. The warehouse is divided into 650 paths, with each 1 meter long and 1 meter wide grid to form a standardized grid map. In the raised map, each shelf measuring 2 meters long and 4 meters wide occupied 8 grids. To ignore the problem of different pallet sizes caused by different materials, each pallet is set as a standard model with a length of 1 meter and a width of 1 meter, and the robot can only transport 1 pallet for each task. Each shelf is separated by a path with a width of 1 meter, which serves as a transportation channel for warehouse robots and is distributed across the whole warehouse. In order to minimize the carrying distance of shelves in the picking process, all the shelves in the warehouse are divided into 3 parts according to the frequency of use. The 2 rows of shelves near the picking platform are high-frequency storage areas for storing goods with high frequency of use, such as life jackets and tents. The 3rd and 4th rows of shelves are minimum frequency storage areas, which store oil, expectation lights, and other goods. The last rows of shelves for low-frequency storage areas, storage generators, and other low-frequency and large goods. In the intelligent storage system, multiple robots participate in the transportation of goods in and out of the warehouse at the same time, and the environment is dynamic and changeable, resulting in congestion, clearing, and even deadlock. Typical cases can be divided into the following 4 categories. In case A, the risk of rear-end collision can be avoided by installing a sensor on the head of the robot and slowing down in advance after receiving the information. However, case B, C, and D still cannot be avoided by using distance sensor. So this paper uses reservation table to solve this problem. When two robots meet at an intersection, it must be decided that one robot first occupies the intersection and passes through it, while the other robot waits in place and continues to move after this robot passes. In other words, each grid can only be occupied by one robot at a certain time. The rest are occupied by the robot in the raster map, and the current time is recorded in the same table to form the reservation table. The reservation table takes the warehouse grid model as the horizontal and vertical coordinates and uses a two-dimensional array to record the states of each cell. The idle table is 0, otherwise it is 1. The grid occupied by the robot at each moment records the corresponding report number, and other robots can decide to move forward and wait for another robot to pass by querying the reservation table at the current time. Before designing intelligent avoidance strategy, it is necessary to ensure that each robot can drive in the optimal path. Here, this paper improved the A-star algorithm to further improve the optimization effect. A-star algorithm is a heuristic algorithm, which is the most efficient direct search method to solve the shortest path in the static map. It sorts the neighboring nodes according to the evolution function, and then selects the optimal neighboring nodes for the next search until the target point. The optimal solution of searching direction and path can be realized simultaneously. The warehouse map used in this paper is simple and neat, which is suitable for using A-star algorithm to calculate the shortest path. The cost estimation function of A-star algorithm is expressed as follows. Its formula Gn represents the actual cost from the starting point to the current node n, which is generally expressed by distance or time. In this paper, time is used as a unified scalar to compare the cost of function fn. Variable d is the actual moving distance of robot from the starting point to current node n, and v is the speed at which the robot travels at constant speed. Variable hn represents the heuristic estimated cost from the current node n to the target point. Variable dn is the estimated shortest distance of the robot from the current node n to the target point, which is usually represented by eluding distance, Chebyshev distance, and Hamilton distance. Here, the Hamilton distance is used. However, in the actual operation process, robots, especially the four-way shuttle robots commonly used in logistics warehouses, need a certain amount of time to complete the reserving action in the turning process. In addition, when the robot encounters path conflict, if its weight is small, it needs to pass and wait for other robots to pass before continue to move. The waiting time should also be taken into account. Therefore, this paper improves the A-star algorithm and applies the cost formula as follows. However, when multiple robots are about to pass the same intersection at the same time, the sequence of robots passing cannot be effectively demanded by the control of the reservation table alone. This paper innovatively put forward a dynamic waiting table to solve the problem of crossing order and ensure that the materials with the highest demand will be given priority for delivery. The dynamic weighting table is a matrix table composed of robot label and corresponding dynamic weights. The dynamic weight is respected by Wi, which refers to the weight of robot Ri at the current moment, where Ri represents the property level of materials in the transportation task currently performed by robot Ri. After receiving the task, the robot will give the rate to Ri according to the type of goods until the end of the task. According to the classification of shelves, goods are also divided into three types here. Ri of goods used in high frequency, minimum frequency, and low frequency are assigned as 1, 2, and 3, respectively. Variable GI means whether robot Ri is carrying goods at the current moment. Yes means robot Ri is in the shipment stage at the same time, while no means not. Variable HNI represents the heuristic time of the current position of our robot Ri to reach the target point. In the raster map established in this paper, 8 robots are arranged. The operation efficiency of A-star algorithm and the optimization algorithm is compared by simulating 40 material transportation tasks in each group. In order to simulate the transportation characteristics of fluid control material warehouse, this paper adjusts the efficiency of the algorithm by comparing the efficiency of high-frequency material shipment, high-frequency material pickup efficiency, minimum material picking up efficiency, and the time of the algorithm. Compared with A-star algorithm, the optimization algorithm improved the average shipment efficiency by 14.89%, the average high-frequency pickup efficiency by 2.89%, and the average minimum frequency pickup efficiency by 15.1%. In addition, due to the addition of the dynamic weighting table, the robot can make quick decisions when it encounters conflicts and avoid unnecessary path plan. As a result, the running efficiency of the optimization algorithm is improved by 75.5% compared with A-star algorithm. In this paper, based on the characteristics of fluid control materials warehouse, an improved A-star algorithm under the reservation table and dynamic weighted table is proposed. The following experiments are completed: building the grid map of the warehouse and dividing the storage areas of goods with different frequency of use, joining the reservation table to prevent the robot from path conflict. This paper innovatively adds dynamic weighting table, which gives property to high property goods and improves the operation efficiency of the warehouse under fluid control, and the stability of efficiency to the proposed method are verified by simulation experiments. Thanks for your attention.